Hey, hello, physics students. This lecture is in chapter 24, and this will be, at least one of two, I think. There's really sort of a lot of really kind of neat physics that shows up in chapter 24. And for those that are, moving on to be engineers, this is, really kind of a nice place to see something very, very simple to create. Um, However, there's just a lot of really, really good physics that goes with essentially two conductors that are separated by a small distance when you put charge on them. And that's this idea of what a capacitor happens to be. And so, we're going to really look at capacitors, their functions, and then, really deep dive into the physics of what's really taking place there. And so that's what's really kind of happening here in chapter 24. Now, a capacitor is a device that is meant to store electric charge. That is its main function. And when you store charge, you're also then really storing, energy as well. And so, those are two important aspects that we're going to take a look at here. So, so let's kind of get started here with this idea of what is a capacitor, and really how do you make them? And we've seen this a little bit already, but a capacitor is made up of typically two conducting plates separated by a small distance. The function is to store charge. And therefore, energy really gets stored on these devices. And there's a number of ways to construct these, and we'll take a look at a few different ways of making a capacitor, and the physics that goes with them, because it's going to be a little bit different for each type of capacitor. And that's something that students who's first encountering this, that's really what you should be doing is going through the different types of capacitors and seeing if you cannot work out really what is the physics, what's important here, and what is it that we really sort of know about these things here. What we need is really a definition, kind of mathematically here of what's kind of taking place. And, this is kind of just a general statement. For really all capacitors. And this helps us define exactly what we mean by a capacitor. And just the name kind of implies that it's kind of holding something, right? And so, we're putting electric charge on these devices. And so the capacitance is not the same as charge, right? Charge is a number of coulombs. Capacitance, though, needs to be proportional to that. That is, when you can put a lot of charge on something, then you have a high capacitance, right? So, if you have capacitor plates that are about the size of dimes, right? Two little pieces of metal that are the size of dimes, there's a certain amount of charge you're going to be able to put on there. Now, if you have like garbage can lids, big metal garbage can lids that are, 2.5 feet across, you're going to be able to put more charge on something like that because of the geometry of the conductor. And if you're thinking this through, what is pushing the charge onto the conductors is important too, right? So if you use a little AAA battery, it can push charge. That's its function. That's considerably different than maybe something like a a battery that might be in your car, right? One of them may be able to push, considerably more charge here. So when you're kind of thinking about this, right, there's different aspects here. And this is something that you really kind of need to memorize. That's really good for any capacitor. That the charge that you can put on the capacitor is proportional to C, which is what we're going to call the capacitance. The amount of charge, though, is also proportional to what's pushing the charge on there. That is the voltage source. A weak, small little voltage source can't get that much charge on there, no matter how big the pieces of metal happen to be. And so, this kind of maybe makes sense here, that we're going to really define C to be proportional to the charge, right? And it's inversely proportional to the voltage. The charge is not, but the capacitance is. Right? So this is a general statement, and memorize that. Q equals C times V. Definitely something that we want to really memorize and know very well here. Now take a look here at these units, and they're not entirely intuitive, right? Q equals C times V. This has to be in coulombs. So now there's kind of like two C's kind of, dancing around here. And V, volts, so if I divide both sides by volts, this is capacitance. So I'm going to write it out so we don't have too many C's here. And C, charge, there's not much I can do about that. Now a volt is a joule per coulomb, and this equals capacitance. And so when I really sort of take a look at this, capacitance equals, looks like coulombs squared divided by joules. Okay, so capacitance has got units of Q squared, coulombs squared divided by joules, and this is called a farad, after Michael Faraday. So he'll be, one of the big heroes of this semester here. And so here are the units of capacitance. It's in farads, and a farad equals charge squared divided by joules. Now capacitance is very close to the idea of kind of what can the device really sort of hold here. So if you've got two little parallel plates and they're small, yeah, maybe not as much charge can go on those as bigger plates if you're using the same voltage source, to do an even comparison here. So capacitance is actually a number that really, if you have like no ability to push charge, no voltage source, no ability to create a hill for charge to move down to go on your plates, capacitance could be a zero, right? We could probably, maybe, or actually that would be the charge could be zero that we'd be able to push out. But capacitance is a positive number. Okay, so for most capacitors in our life, it's a very small number, something like a millionth of 1 farad, a billionth of a farad, maybe a trillionth of a farad, very small numbers. And, a lot of devices here is my calculator, and I think most keyboards, how does the electronics know, when you hit 7, that you're actually hitting 7? But, typically, one way engineers kind of work this out is that the 7 is a certain size capacitor. And when you hit that 7, the charge, can get released into a circuit, and then, the circuit recognizes, exactly that is what you hit. So what you're really doing in these circuits is kind of counting electrons that are, moving around and so forth here. But capacitance is for something like a calculator, a small number, right? These are going to be very, very tiny capacitances. So something like a trillionth of a farad, is not unusual. And so you can have picofarads, we can have nanofarads, times 10 to the minus 9, and these are pretty typical numbers. Now, in a normal course, I would bring some capacitors in for you to take a look at. And a lot of times you can't see much because they look cylindrical and they're all encased, right? But I've got some that are, probably, a foot tall, and they're probably 3 or 4 inches diameter, and then they have a number connected to them, their capacitance. And then I've got some really small ones, and on some of the small ones, the capacitance is actually bigger, which is kind of maybe amazing. But we'll see, how that is, how the engineers, construct the capacitors to maybe be smaller, which is more convenient for your circuit boards, but then still hold more charge if it's the function. And some capacitors can get expensive, but typically they're not. But, I've got some that are about the size of a quarter in diameter. And, they might cost you $50, $60, $70 because they're actually 1 farad capacitors, and those are giant capacitors. And a lot of times stereo system might need a capacitor like that in line because speakers have a difficult time pushing low notes. They have usually no problem with the high notes. And so if you have a capacitor sort of in line, and here comes this very low frequency, something can trigger then that capacitor to dump its charge, and then there's more charge going to the speaker, and then you get this thumping that you can feel from 2 blocks away, right, at 2 in the morning and stuff like that. So, so those types of capacitors are, can be very expensive because they hold a huge amount of charge. And maybe a different place that you see capacitors would be, a lot of times on a camera, there's a flash, right? And so, my phone, she talks to me, if I take a picture and the flash goes off, and then I want to take another picture, she starts yelling at me that, the device is not ready. And because there's a battery in there, you're pulling charge from the battery, it's going to the capacitor, and it's there to dump into the flash when the flash is needed. So when the electronics say, oh, it's dark enough, I need the flash, you need a bunch of charge then to be able to run to that spot and then make this bright light. The capacitor does not get charged up immediately. This will be an issue that we will look at in some very, very mathematical detail, right? And so if you push a charge onto a capacitor plate, the first one's for free, but now the second one, the second charge you try to push onto the plates is being repelled by the first one that was there. So you got to push harder, right? And so we're going to, take a look at, all these sort of aspects of what's taking place here. But at least conceptually, there's probably many ways you can kind of think your way through something like this. And, the net effect is really the important thing here. But, if you have like 2 plates here and you have a voltage source, which is typically a battery, right? So you've got a voltage source, and, it's got a top of the battery, it's got the bottom of the battery. If you get the top of the battery, you connect it to that plate, and you get the bottom of the battery, and you connect it to that plate. The battery then has this ability to push charge, because really at the top of the battery, say you have a whole bunch of positive charges there, and they're trying to get away from each other. And now you connect up a wire, a conductor, and then they can see this plate. They've got more places now where they can move away from each other. So as the battery essentially pushes this first charge here, there's a couple ways to think about this. And once again, the net effect is the important thing. You can think about that positive charge as knocking off a positive off the other plate inductively, right? And so a negative pops up. Or you can think about the bottom of the battery as pushing out positive and negatives, positives out one side of the battery, negatives on the other side. And the plates will always have opposite charges, and they will always be in equal amounts. That's the net effect here. So the battery has no problems with the first charge because there's nothing downstream that's pushing back. But now, if you sort of imagine now the second charge is kind of moving in here, it sees the first one, and that's a problem, all right, because now it's being repelled. Now, the first charge, if you think about that as a point charge, And the voltage of a point charge is K times Q divided by R, the distance that you get within it. So as this charge coming out of the battery gets closer, right, the voltage, gets bigger, and then they start repelling each other. But the voltage of one point charge is typically going to be much smaller than the voltage of the battery. So the battery kind of wins this energy fight here. But when you kind of put your second charge down, then the two charges probably will be as far from each other as possible. So they might look something like that. And then maybe you end up with this configuration. And and so now when you push the third charge onto the plates, it's even harder because you're pushing against two charges that are sitting there. But if the battery has the pushing power, has the energy, then it adds this third charge, and it might look something like that. Eventually, the battery pushes charge out onto these plates until it can't really push anymore. And at that point, when the capacitor has Q total, the total amount that it can have, which is a function of, I'm looking in this green box, C, the capacitance of the system, times the voltage. At that point, the voltage between the plates is the same as the voltage of the battery. Everything now is equal, right? The battery just kind of keeps pushing charge out. And as it pushes more charge out, sort of the hill, the voltage of the plates gets higher and higher and higher, and eventually it equals the voltage of the battery, and now charges can't move anymore because now there's no hill, right? Objects move because there's a net force on them or there's an energy difference. And so the net effect is the voltage between the plates is that of the battery. So you can, at this point, once it's totally filled, you can disconnect the battery and the charges just sit there, which is why when I bring in capacitors into class, you can't really see what's going on because it's encapsulated. And so what you have to do is wrap some material around the plates so the atmosphere can't get to the charge. So the charge will just sort of sit there. And capacitors can hold charge for weeks, months. And so when a technician goes into something like an amplifier, one of the first things they will do is get a couple of wires, maybe with a light bulb connected to it, and they will go across the capacitors. And then when the light bulb lights up, they know there was charge there, and then the positives can see the negatives. So you're just getting a wire and connecting the two plates together, and then they neutralize, right? And now you're making it safe. Otherwise, you're going in there with your hands and tools, and if these capacitors have a lot of charge sitting there, that can be very, very dangerous. And the device is not plugged in. Maybe you haven't had it plugged in for a few days. It doesn't matter, right? The technicians will know this, and they'll know exactly how to get rid of the charge here. So some interesting aspects. Do remember what we have here in green. Do know exactly the units here of capacitance. And we're going to see exactly what capacitance depends on, but it probably will not surprise you. If you think about a couple plates and you're putting charge in there, and you go, okay, well, C for that configuration, the capacitance of that, what is it going to depend on? And as you start thinking through this, I think you're going to come up with some different variables that might be important here. But the physics will tell us exactly what's important. But I think it's not that hard to guess here. Okay. So let's take a look at probably a parallel plate capacitor is probably a good place to start because the physics there is a little bit easier when you've got parallel plates. It's the one place that we get a constant electric field, and that just makes the math easier, right? When you're dealing with constants, you're not dealing with the calculus and things like that. So, this might not be a bad place for us to really kind of begin here. So, the electric field of a parallel plate capacitor, a number of ways to kind of go through and do this. But, a typical way would be to, get your Gaussian surface in here and put it right inside the piece of metal here. And when you do this, you really have two end caps, and then you have the round part of your Gaussian surface. And so when you start forming E dot dA to find the electric field here, you're really considering three different areas here, right? You really have, maybe area 1, you've got maybe area 2, and then maybe you've got area 3. It's only area 3 turns out to be the important one, but when you really do kind of start looking at this in detail, you say, well, the electric field here is E dot dA, and so there's a dot product, but the integral implies adding up, all of the contributions, and so you have this area, and the area is kind of complicated when you draw these cylinders here. And your Gaussian surface has to be closed. So, that's what this little round circle means here. And so we have this can, essentially, right? So it's a closed surface here. And so when we do this, we really kind of have this, over surface 1. You have it over surface 2. And you have it over surface 3. And surface 1, surface 2, and surface 3 are not closed surfaces, right? They're just areas, but they make a closed surface. Now, so, the hard part with Gauss's law is that, there's a lot of concepts that kind of get involved here. And when it comes to that first area, that end cap that's inside of the plate here, I know there cannot be this, right? This electric field kind of pointing out here like this. And I've got an area element that points out like this. I know that electric field has to be 0. Otherwise, there's an electric field inside of the material, which means the charged particles are being pushed inside the material, they're accelerating, and they're just constantly moving, because what's there to turn off the electric field? And what you have then is perpetual motion, these charged particles, and this defies our laws of thermodynamics and so forth. So you really sort of know then this first one is 0, and so you really kind of do that conceptually. And area 2, if there was any sort of vector coming out of area 2, say if there was an E field doing something like that, and maybe the area vector looks something like that, has to be at right angles. Once again, if there's an electric field that's pointing along the face of the plates here, then the charged particles are once again in continual motion, on the plates, and they're not in equilibrium, and so that just can't be. And once again, you would have really kind of almost like perpetual motion here, and so surface 2, we get really no contribution. So it's really through this third face is really kind of the the important one. And so I've got an electric field here, and I've got an area that looks something like that. And I know the electric field here can't be cutting through there at anything other than a right angle. So if I kind of blow up area 3 here, and that area element is defined to be at right angles to that surface. Now, if you're thinking, well, why don't I have an electric field kind of pointing like that? And this would have a component that I might maybe call the X direction. It would have a component here in the Y direction. And it's this one right here is the same as this one down here that I just drew. That would imply that there is some sideways force on these particles, and they're locked, right? They're locked. They're sort of locked in Mortal Kombat, and they're pushing each other, but all the forces are balanced out. It's like a house, right? You kind of throw all the widgets out there, and the house kind of builds itself very fast within about a millionth of a second, and all the forces now are balanced, right? There's forces down in your house, all the weight going down, there's beams holding up, and nobody moves, right? Nobody's moving here at all. So I know that E must be really coming out of this thing. So the only component that really, is left standing is this Y component. So, the net electric field here has got to be, doing something like that. And so, inside of these plates here, and what we'll see in measurement probably in a week or so in the laboratory that, we'll get is a very, very constant electric field there. So what you do is, you have this E field and there is this dot product, but E and A line up. So, E times A times the cosine of the angle between them here is going to give us, because that A is a vector, all these spots here, is going to give us a 1. And so, when you add up this right here, when you add up the area of that end cap, you just get the area of the end cap, right? That's what the integral is telling you, right? Get your little tiny areas, add them all up, and you end up with the total area here. And that's the charge enclosed all over epsilon 0. Now think about this. You may draw your Gaussian maybe differently than I drew mine. You might have drawn it, let me get a different color here. Right? Somebody might draw this thing here much bigger, and your little cylinder might look like that. And when you do that, what you've got is a bigger area, but you've got more charge in there, right? And so it doesn't matter, right? Because the Gaussian just exists really in your head. So typically you're trying to make the Gaussian disappear out of your results. Because it's just kind of arbitrary here, but E, and then this is just the area of really the end cap that I've got here. But that enclosed some charge. And so, the electric field here is the charge that's enclosed in my Gaussian divided by the area kind of that end cap. And then I've got this, 1 over epsilon 0, the permittivity of free space, how the electric field is going from one side, to the other side, and there's really nothing here that's getting in the way here. But for the most part, the amount of charge I've got enclosed in the size of my Gaussian, that can be written as, in what people typically do, write this as sigma, where sigma is the charge per area. And so it doesn't really matter how big of a Gaussian you choose, because the charge per area, it's all uniformly distributed across the plates here, right? Everything gets locked into this equilibrium positions. And so it doesn't really, make any difference here how big the Gaussian is, because this is a constant, for the material. So if you draw a little one, you have a small amount of charge, but then you have a small area. But that ratio is still the same for any size that you happen to choose. Now this right here might turn out to be kind of handy here in a little bit. So I'm not going to kind of forget that either. But here's really kind of the electric field here. And what I'm going to try to do here is figure out what the capacitance of two parallel plates happen to be. And if you're kind of watching what's happening here, this is pretty typical. This is a good strategy to have. To find the capacitance, find the electric field. If you get the electric field, then you should be able to find the voltage between the plates. If you know the voltage between the plates, you should be able to end up with a capacitance. So in the back of my thinking, that's what I'm really going to try to do here. So you might kind of want to take note of kind of the sort of the idea here is get the electric field. Then try to get your hands on the voltage between the plates. And then lastly, turn that into the capacitance of the system. Okay, and so here, getting the electric field was not that bad. So Gauss's law kind of makes, short, work of this. Now, what we've got going for us here is we have some constants here. And so, I might kind of call all of this getting this electric field here. So maybe I'll call that 1. That's kind of step 1 here. Get that electric field. And step 2 is, kind of get the voltage, or use the voltage relationship here. Get the voltage difference between the plates. And, a lot of times students will really kind of get really hung up on voltages being a positive or negative or whatever. It's just voltage differences are really the only important thing here. So it's possible that a voltmeter may say -3. So if you get a voltmeter and you get like a C battery, and you touch the top of it and you touch the bottom of it, it may say -3 volts. And it tells you that there's 3 volts difference between the top and bottom. The minus sign goes away if you pick up your wires and you connect it up the other way. And that's just because the meter is trying to see it a certain way. But it still tells you there's a 3-volt difference between the top and the bottom of the battery. And that's the only thing that's important here. Capacitance cannot be negative. So when I start finding voltages here, I'm going to really kind of take like absolute values, right? Because there is no concept here of any sort of negative capacitance here. And so, I kind of know in between the plates here that, and I could just be looking at units here. So recall units. They can tell you a lot. The electric field is in newtons per coulomb, which is equal to volts per meter. Okay, and so this was part of the previous chapter here. And so the electric field being constant, and that's the only reason I can do this, because I have a constant electric field, allows you to, make the mathematics kind of short and quick here. We have a constant electric field. And so take a look at the units here. The electric field times D, and that's the distance between the plates. So if I'm thinking about the E field being in volts per meter, times meters gives me the voltage difference, right? That gives me the voltage difference. Get the electric field, we got that. Try to get some sort of a handle on what the voltage looks like. Well, I've got something sitting right here in front of me mathematically, and then I should be able to get the capacitance. So that'll be my third step. So how do you get the capacitance here? So you're going to now get the capacitance by using, and you might have to be clever here. In this case, I'm going to use Q equals C times V. So I'm going to use that general statement that works really for all different types of capacitors here. Okay, so Q equals C times V. Okay, so can you be clever enough here to kind of figure out what's taking place here? And so, if I look at this over here now, this V implies a difference, and so it's really a delta V, right? It's always from one place to the other. So it's really from one plate to the other plate is your voltage difference here. But my voltage, or my delta V here, is the charge per capacitance. And this voltage is the same as the electric field times the distance between the plates, right? In that electric field, we just found it up above here. And here because I know what I'm heading for, I'm going to use this version right here that I'm kind of highlighting here in kind of a purple here. And the reason I'm going to use that because it has Q in it. And it's typical that people look at capacitances, without this Q showing up here. So here's kind of the charge, per area, and then, times 1/epsilon 0. That is the electric field, or, one version that we can write it at. And then you've got this D right here. And what I really kind of want to see happen is this step right here, that Q disappears out of here. Okay, because my Gaussian may have only had a small amount of the charge. It may not have had it at all or anything like that. So typically your capacitance, does not rely on what Q you happen to have enclosed in your area here. But what I could have done is I could have made my Gaussian the entire size of the plates. Then I would have the total amount of charge enclosed, right? And then that area that I see right here would be the area of a plate. And the other plate has got the same area, but whatever is happening on one plate is the other plate. So if you really kind of think about making your Gaussian giant here, and then you would have the full area of the plates, and that's kind of nice to kind of think about it like that, right? So, that's probably worth, making note of, if the Gaussian maybe encapsulated the entire plate, that implies that, Q that I have enclosed is Q total, that's on a plate, and then the area would be the area of the plate. We'd have that whole area there. And so this might not be a bad way of kind of going about, taking a look at this here. And so, when all is said and done here, if I solve, I'm going to multiply both sides by C. So I have that, and then I'll multiply across by area, epsilon 0. And then I have to divide both sides by D. And this is for a parallel plate capacitor. So there's a statement that tells us the capacitance of a parallel plate capacitor. And so take a look at that. It looks very simple. Area times some sort of electrical constant divided by the distance between the plates here. But there's really two things that you should take away from this, because in any type of capacitor that you're dealing with, you will see essentially the same elements keep showing up. The function will always look different, but you always see the same elements here. A and D, those really describe how big the plates are and how close or how far they are. In other words, just about the entire geometry of the plate system here is showing up here, right? And so when you really kind of take a look at this here, these two guys right there, that has to do with, the geometry of the plates. And this guy right here, that is telling us there is nothing between the plates, which might imply that if we put something between the plates, the capacitance may turn out to be a different number, right? And so this really means that there is no material between the plates. Those two elements show up time and time again. And what are the two elements? The geometry of the plates is typically important, and the material that you put between the plates is typically important. And we will see that always kind of show up here. And so this is something that typically, probably, probably electronic engineers, they're going to know this right here by heart, that the area of the plates times, some sort of constant that is connected to whether there's material there or not is important. And then the distance between the plates. So it looks like if the plates get close together, the capacitance of the system goes up. Oh, okay. Why is that? Well, maybe you have stronger electric fields, right? Because the electric field is the voltage, which is set up by the battery. That's kind of fixed, times distance. And so the distance is big, maybe you get bigger electric fields, and that helps the capacitance here and so forth. Okay, so kind of interesting, but this is a very good strategy right here. There's other strategy you can use here, but if you can get the electric field between the plates, turn that into the voltage between the plates, then using Q equals C times V, you should be able to kind of play around with the algebra and end up with something that says C equals a bunch of stuff. That bunch of stuff almost always will have geometry and materials that are between the plates. Eventually, we will put material between the plates, and that will be called a dielectric. And a dielectric is a fancy name for an insulating material, right? You can't put conducting material between the plates because then the positives will see the negatives and then they just neutralize, and then you don't have charges sort of just sitting there. And that's what you really want. You want them sitting there in storage, and then you can dump them and use them to do some work for you, at your convenience, which might be hitting a button on a keyboard or something like that, or on your calculator here. Okay, so there is kind of the story here between the plates on a parallel plate capacitor. Now, when you put charges on the capacitor, it takes you work to do that, right? The first charge you get to put there for free. After that, the battery is working because there's already charges downstream and you're trying to push more into that region and they're repelling each other. So, the battery kind of starts with a hill and the capacitor has sort of no hill. But as you start, dumping charges here, that hill starts getting bigger and bigger and bigger. And eventually when the two hills are the same, everything's at the same potential energy. And now no more work can be done. Okay, and so eventually, once the plates are charged up, you're really kind of done. But then you can unhook the battery and the charge to stay there, especially if they're well insulated from like the atmosphere. Right? There'll be no air molecules to come along and kind of steal some charges and things like that. So when you do that, you have a large number of charged particles in close vicinity of each other. And what that really means is that you've got energy stored sitting there, right? So now there's energy sitting there because those particles want to move, right? It's sort of like, getting a spring and kind of pulling it apart. And it's just sort of sitting there. These particles sitting there. And if you let go, right, something wants to move, right? If they have the ability to move, they will. And, what do they need to move? Well, they need a conductive path, right? They need some place they can move with very little friction and so forth. But the important thing here is that energy gets stored in the capacitor, right? And then we'll take a look, at where is the energy and how people think about that and so forth. Okay, so let's take a look at this idea of energy stored in a capacitor. Probably a lot of different ways to kind of think about this. I'm not going to worry about too many of the technical mathematical details here, but if you've got a set of parallel metal plates and you have a voltage source, right? So we've got some sort of battery here, and you connect the battery up. That first charge coming from the top of the battery, the second charge or the negative charge coming from the bottom of the battery, maybe it looks like that. And what ends up happening now on that plate, you have a voltage now. Now there's a voltage there because there's a point charge there. Okay, so maybe you kind of call that like V1, right? There's now a voltage because there's one charge there. Now, when the battery pushes the second charge out, the voltage just changed. Now you have 2-point charges sitting there, right? So the voltage keeps getting bigger and bigger and bigger until it equals that of the battery. Once it equals that of the battery, then no charges can move anymore, right? Everybody's at the same energy level, and there's no hill. There's no more hill for anything to move down. And so, if you're looking at, this general statement that really tells us a lot about what's going on in a capacitor, Q equals C times V. The capacitance, now take a look at what we have here. For a parallel plate capacitor, it has to do with the area of the plates. Well, that's not going to change. The material between the plates, that's not going to change. And the distance probably isn't going to change. Now, there are some very clever devices out there where you can get a number of plates and you can rotate them in to be very close to each other or very far, and then you have a variable capacitor. But for the most part, C of the device, the capacitance, is a constant unless you are changing distances and geometries and things like that. But most of the time you kind of think about the C as being a constant here. But when I kind of put charge 1 out there, right, I've got a voltage. Maybe I'll call that voltage 1. Now what you really want to do to charge up the capacitor is you need to put a little bit more charge in there. Just kind of keep doing that, right? And so kind of what you want to do is maybe put sort of a small amount of charge on the plates and kind of keep adding that up and adding that up and adding that up. And so when you do that, maybe you've got Q here, and I'll divide maybe both sides here by C here. And I'm going to put a little bit more charge on one side. And, well, I've got to do the same thing to both sides in an equivalent statement. Now, take a look here at what's happening unit-wise. This right here is joules per coulomb, and I'm multiplying it by a little bit of charge that I'm going to be moving here, right? So you're going to put like just a small, right, another point charge, a little bit more charge over there. And the multiplication of those two starts indicating that there are joules sitting there, right? It's a measurement of what? Really how much work the battery's done at that point in time. And so, I'm kind of noticing this right here. This is joules, which implies, this is work being done. And so that's what the battery's doing. It's pushing stuff uphill, right? It's pushing stuff uphill. The first one it gets for free, but after that, you're pushing charges uphill. Eventually, when it's done, the work that the battery has done will be equal to the energy stored in the system. If these are good conductors and there's no friction here to worry about or anything like that, eventually, once everything is charged up and you have full charge sitting on the plates, as much as you can get with that voltage device, then the work done will equal really the energy stored. And that should make sense. It's really no difference than lifting a box up in the gravity field. When you lift the box up in the gravity field and you put it on a shelf, the work that you did is now equal to the object's potential energy in that position. So the energy is still there someplace in the universe, and it's locked up in the gravity field with that object's location in it and so forth. I think what I'm going to do here is call this over here then work. Right? So this is the work being done. And what I'm going to do over here is add up all the charge all the way up to Q total, the total amount that you can get. And so you just kind of keep putting little point charges out there, little DQs, and you just kind of keep adding them up. And in this case, I'm just going to assume that our capacitance is just a constant here. So the capacitance really passes out of my integral sign here really kind of for free here. So that kind of comes out. And so Q will get squared. I'll divide by 2. And I'm going to go from 0 to Q total here. And that's the work done. which eventually equals the potential energy that is stored. Now I'm going to call it PE. Your textbook starts calling it U, but there's V's around, there's U's, and sometimes when you're handwriting things, those things can look, pretty similar here. But your potential energy here that gets stored looks like 1/2 Q total squared all over C. Okay. So, is that surprising? Well, I kind of think that, the more charge I can get on the plates, the more energy I should have stored. That really is kind of making sense to me. Now, take a look. It's inversely proportional to the capacitance of the system, which might be kind of surprising. But if you think about that, you might be able to kind of see why that might be the case and what's going on there. Now, what I'm going to do, what's floating around the back of my head, though, is always this general statement here. Q equals C times V. Keep saying that to yourself. You walk out to your car, Q equals C times V. Q equals C times V. This is good for, lots of different capacitors. I'm going to use that just to give me some different ways of looking at the energy that is stored in some sort of capacitor here. And so what did I do? I called this up here. Let's call this, maybe number 1. And I'm going to come down here. I'll call this number 2. And my potential energy is 1/2 Q total squared all over C. And what I'm going to do, I'm going to take out Q and in its place put C times V from here. Okay, and it gets squared. And so when I do that, I have another way of writing the potential energy, but now not in terms of how much charge is there, but in terms of the voltage source, because eventually the plates get up to that voltage and then everything stops moving. And so, when I do this here, I guess I have a 1/2. I have a C down here. Now on the top, you get C squared V squared. And so I could write this potential energy here as 1/2. It looks like that C cancels one of those. 1/2 C V squared. Very amazing, because you have seen energies before that look like this mathematically, functionally, right? You've seen kinetic energies that look like 1/2 mv squares. You've seen energy stored in a spring that look like 1/2 kx squares. And now energy stored in a capacitor is 1/2 CV squared. And so this is, kind of an interesting mathematical form that seems like nature really kind of likes this here. And so I think if you're still, clever on, doing some algebra here, what we could do is go back to where we started. Potential energy equals 1/2 Q squared. And I'm going to drop the little total now because I think it's going to be implied that this is when the capacitor plates are fully charged up. And what I can do is not take Q out, but I will take, using my general statement there, I think I'll take C out. And so I'll leave 1/2 here. I'm going to leave Q here. And it looks like C can be written from above here. So if we kind of come in here, it looks like C equals Q all over V is what C happens to be equal, looks like to me. Yeah, Q divided by V equals C. So I'll take C out and I'll put Q all over V here. And so when all is said and done here, I have a 1/2, and I think this Q takes out one of those Q's. And so then you end up with a Q on the top, and you have a V on the bottom of a fraction on the bottom of a fraction. And so here's another way of writing the energy stored in between the plates on a parallel plate capacitor. So, you just kind of use whatever is convenient. If you've got Q's and V's, okay, we use the last version. If you have C's and V's, you can use that second version. And if you've got Q's and C's, you can use that first version. Now, you should probably take a minute or two and convince yourself that when you put in the correct units for Q and V in this last version, number 3, or in what I have boxed up in green, put in the right units for C and V, and U square V and so forth, that every time that you do this, right, you're going to be ending up getting joules, right? So you should always be getting joules for all of these, different energies being stored here. Okay, so, maybe a question comes up here now is, okay, I put a bunch of charges on plates, and it takes me work to do that. Now that work can come back to me in terms of moving charged particles, right? Eventually it can come back in terms of their kinetic energies. And that's what we use, right? We use the motion of the charges to do work for us. And since the forces here are so big, right, they can make a lot of stuff move. Right? So it doesn't take very long to rub a piece of wool on a piece of plastic, and you can lift pieces of metal up on electroscope leaves against gravity very easily. Where is the energy? So if we're storing it, where is it? And so it's probably worthwhile to kind of contemplate that question here. So, where is the energy? And I think to maybe answer that, I'm still really just looking here at parallel plates. So what do I know about parallel plates? Well, I know Q equals C times V. That's going to work. I know exactly what the capacitance of a parallel plate capacitor looks like. So the parallel plate capacitor, I've got epsilon 0 times the area of the plates divided by D. So I kind of know that's true. I know that the electric field here is volts per meter. So that's volts per distance. And I know that the potential energy that is stored there, and there's different versions. And so see, I'm looking at what I've got here. I got V's and stuff. So I'm going to use this one here, 1/2 CV squared, because I've got a C here and I've got a V there. So I'm going to use this last version here. Right. So let's take a look here. The potential energy is 1/2 C times V squared. So 1/2, and C for a parallel plate capacitor is that right there. Right? And then I'm going to use this, the second statement, that the electric field is V over D, to substitute out the voltage. And so I think what I get here is E times D, and there's a square on that. So let me take a look-see here and see kind of what's left over when we do this. So there's a 1/2. You're going to have epsilon 0, A, and D, so not much happens there. And then you have E squared and you have D squared. So that D is going to take out a D here. Okay, and so what's left standing here is a 1/2 epsilon 0, and I'm going to get A times D, and I have E squared here. Okay. This to any physicist is familiar in this aspect, that the energy stored in a capacitor will typically always look something like this. Now, this is for a parallel plate capacitor. Okay. But what I see here are some aspects that will translate to any type of capacitor. And we'll take a look at some different types of capacitors here. What is this right here? That's the area of the plates. So they could be round, they could be square, they could be rectangular, makes no difference, times the distance between them. And so if you really think about that, right, the area of the plate and then times the distance to the other plate, this is really the volume, right? This gives you the volume, kind of between the plates. And I think most physicists are going to recognize that the potential energy has something to do with the volume between the plates. And for any capacitor, the potential energy stored there will always go as E squared. So that's something that's pretty normal to really kind of see that for the potential energy always going as the electric field somehow squared. That typically plays out for any type of configuration that you really sort of build here. And so, you kind of go back to this question here of, where is the energy? And, take a look here. The energy can be thought to be kind of in the electric field. And why is there an electric field? Well, the charges are putting forces on each other. That's where the energy is, right? That there is the ability for these particles to push each other, make themselves move, which gives you kinetic energy. So this potential energy can get turned into kinetic energy if you give them a conducting path to do so. And so usually people look at this and say, the energy is in the electric field that gets created by putting all the charged particles there on these plates and kind of keeping them there, in this close proximity to each other, because there's this electric field, right? There's this Coulomb force between the charged particles here. So, this right here, I think when I'm studying capacitors, this is something that's probably well worth, kind of keeping in mind here. That the volume between the plates is important. A lot of times you will see people who are experts in this talk about the energy density, which is the potential energy divided by the volume. And so then you get really then joules per cubic meter. And, they're going to talk about their capacitors sometimes, in that fashion. And so that volume here, recognizing that A times D is a volume, could be important here. So some very nice physics playing out here just by getting two pieces of metal and standing them off a small distance and hooking them to a battery. And you push charges onto those plates. And those plates then get Q on them, and that Q depends on how hard you push, right? Your voltage source, but also the capacitance of the system. So the capacitance of the system for a parallel plate capacitor turned out to be somehow importantly connected to the geometry of the plates, as well as any material or no material between the plates here. And so I think I want to try to use what we've got here and look at a different kind of capacitor. And so if there are little aspects here that are kind of bothering you, this might be a good place to hit pause and kind of go back and just kind of look at the sequence and the thinking here of what's taking place. That you really start off with Q equals C times V, which is really a definition of the capacitance of the system. And then you just kind of slowly start, looking at, if I'm going to put charges on something that looks like this, what's the electric field look like? What's the voltage between the plates? You should be able to come up with the capacitance. And then we're able to, get some sort of energy relationships here that really work for any type of capacitor here. So, okay, let me get some more energy and think about this here. And what are we going to do next year? Okay, so you might have this sheet in your package of stuff. So if you don't have it, hit pause and grab this. So we have a spherical capacitor, which are concentric, sometimes shells or not. And so you have an inner conductor and an outer conductor, and somebody's asking you to find the capacitance. Okay, let me wet my whistle and give this some thought here. I think I'm going to kind of use kind of the same strategy here of that. Oh, in fact, I think what I might do here, just because I think it's instructional, I'm going to use that same method we just did. And that is, get the electric field between the plates. all the action here is taking, in between the plates. And then I'm going to get the voltage difference between the plates. And then I'm going to use that to get C. So that's kind of what we just did, for the parallel plate capacitor. And there's another way of doing this. And, there's always, different ways of looking at stuff because there's a lot of relationships here. And method 2 here might be, if you're clever, you can use energy to do most of your physics. And so it's kind of worthwhile to think about, doing both. And so, really kind of the brute force straightforward one is method 1. And, you should be able to right now that you've had plenty of practice in chapter 22 on Gauss's law. You practice that in chapter 23, getting voltages from one place to the other. And so really, step A and step B in method 1, are something that is, very straightforward to do. And then you just use Q equals C times V typically, and you can get, some sort of expression for the capacitance. So now remember, on a parallel plate capacitor, the capacitance depended on like stuff between the plates and the geometry of the plates. And I would expect it to kind of come out to be the same here. And so I'm going to get the electric field between the plates. So my Gaussian surface, is going to be, some sort of three-dimensional sphere. And I want it to be in between the plates. And so it has, a certain size, right? My Gaussian surface has a certain size. And I'm just going to kind of go right through the steps here. So let's just call this here method 1 here. And so we're going to get the electric field. And so I'm going to use Gauss's law, E dot dA. So there's always some conceptual thinking that goes along this, especially with all the vectors and things like that. Now, I've got positive charge, right? You've got this plus Q right here that I'm circling enclosed. And so, if you're a little positive charge in here and you see that, you have a whole bunch of positives piled up on this inner conductor, you're going to get pushed, sort of exactly away here. Now, I kind of want to be careful. I kind of don't want that electric field line really to kind of go through that outer conductor, because I know on conductors in equilibrium there'll be no electric field here. But E, really points in that direction. So I'll put a little E in there. And then a little area element has to be at right angles to the surface itself. So E and A line up. So the dot product really gives me a 1 here. And as long as I stay that distance away from the inner conductor, I don't move further out or move further in. So it's really radially dependent. When you get closer to the charges, typically the force is bigger, right? You get further away, then usually the force is smaller. But if I stay that distance, then my electric field will be a constant. And the area of that Gaussian is a 4 pi r squared, right? So yeah, that doesn't look like, anything too dramatically different than anything that we've done before. And I've got plus Q enclosed, and I've got this little epsilon 0 here. Okay, so eventually we have to get the voltage. That's kind of the second step here. So I'm kind of thinking, that it might be worthwhile to write, the electric field here as 1 all over 4 pi epsilon naught, right? So that's the same as the Coulomb constant. That's K. And then I've got on the top plus Q, and then I have R squared on the bottom, and this is radially outwards, right? So my electric field can be written like this. And I think I'm just going to write it like that because I know eventually I'm going to have to integrate this thing. So just kind of having, you know, something that looks like, you know, powers is pretty easy to kind of handle there. So, so looking here, yeah, I think everything looks good here. 1 over 4 pi, I've got a Q enclosed and looks like it's 1 over r squared, or the same as r to the minus 2 here. Okay, so let's kind of go to our second step here. Get the difference of volts between the plates. And once again, you know, it's worth remembering that it's only voltage differences that are important here. And so you really want your voltage to kind of come out to be positive because it's going to go into Q equals C times V. And if you kind of carry on with negative signs and things like that, then it'll look like capacitance is negative, and we have no concept of negative capacitance here. And so, yeah, I think I'm going to just use the definition here that voltage is a minus sign of E dot ds. And it looks like everything here is radial, right? So ds, this is a line integral, right? You're integrating along a line. You're going from this spot to that spot in a line, you're this way or that way. But the limits of integration tell the integral really which way you are going. And so in this case, you know, ds really equals dr, because I'm really going to go from one plate to the other plate. So I'm really changing my radial distance here. So, you know, that ds is kind of a dummy variable. It could be a dl, it could be a dr. In this case, you know, it looks like it's going to be some sort of dr here. And so, you know, my voltage difference here, I've got this minus sign. And I think, let me look at this here. I think if I start at R2 and I go to R1, it doesn't make any difference. You can go from R1 to R2 or R2 to R1. I think if I start at the outer one, I go to the inner one, I think this will come out positive. If not, then I'm just going to throw away the minus sign anyway. So it'll make no difference here. Now I've got the electric field here. That's going to go in here. 1 over 4 pi, epsilon naught. I've got Q that's enclosed, and I have r to the minus 2, right? So here is the electric field right there. So that's got to come in here. And then we have a dr, okay? And so Q is a constant once it's charged up, right? Once it's fully, now Q can be a function, right? You could look at a function of time because you start with no charge and eventually you have this thing charged up. But if it's fully charged, then Q is a constant. It's going to pass out of the integral sign. And so, you know, you have this Q, you have 4 pi epsilon naught, and you have r to the minus 2 dr. And so that's actually, you know, fairly easy to integrate. So the power is going to go up by 1. From minus 2, it'll go up to minus 1. And you then divide by the new power, which is minus 1. And let's see, I kind of thought through that kind of quickly, but let's see if I kind of did that correctly. So, you know, this minus sign that's built in, that's, you know, that's this built-in one here to the definition, because we could have minus charges or plus charges here, and, you know, you could be coming with the field or going against it. And then this is from the integration that when you do it, you know, you have r to the minus 2, it becomes r to the minus 1, and then you divide by minus 1, so you have this minus sign. Those two are just going to undo each other here. And so, you know, what you're left with here looks like is Q. And I could call this K, and, you know, it might make things a little cleaner here. And, you know, I've got that minus that one I put in my limits of integration. And so let me take a look, see here. Yeah, see now R1's a small number. And so let's just imagine that R1 is in arbitrary units 2, and R2 is a bigger number like 5. And so if you have 1 over 2 minus 1 over 5, that comes out to be positive. So it looks like I kind of guessed right on how I was going to do my limits of integration. If it came out to be negative, then I would just, get rid of the minus sign anyway here. And so it would make no difference here. So I think we're, through the hard part here of, get E between the plates. So we've got that. We have a voltage statement now between the plates. What's the voltage from one plate to the other? And now I'm going to use that to get the capacitance of a spherical capacitor here. Okay, so now I'm going to use probably just this general statement kind of gets you pretty far to get C. Okay. And so Q equals C, and then V, your voltage difference, looks like Q all over 4 pi epsilon 0. And then I've got this 1 over R1 all over 1 minus R2. And this is kind of what you want to see happen here. Right? You kind of want to see the charge on the plates go away, because you really want capacitance to show up as kind of what we saw before. Really something that has to do with the stuff between the plates and the geometry here. Now, this is a spherical capacitor. So when it comes to spheres, what geometry is important? And if these are, spheres, I think the radii are the only important thing, right? And so I think I see both of those radii sitting right here, right? So this comes out very, very nicely. So I'm going to multiply both sides here by 4 times pi times epsilon 0. So I'll multiply both sides by this, because that will then cancel that. And then it looks like I have to divide each side by this 1 over R1 minus R over 2. And so I can divide, both sides by that, I suppose. And so there's your capacitance. Now, I think you could kind of come in here and maybe do some algebra and kind of clean this up and so forth. But take a look, see what you've got here. Right. So I kind of like what I'm looking at here, because R1 and R2, once again, that's the geometry of the plates. So that's showing up. And then, once again, stuff, whether there's stuff between the plates or not, is kind of showing up. But this is only good for a spherical capacitor. And that's it. But these steps kind of get you pretty far. That this is kind of a nice way of doing that. Right? Find the electric field between the plates, find the voltage between the plates, and then you use Q equals C times V, and and see if you can't just go to a blank piece of paper and just kind of come up with all this on yourself, by yourself, and it should be pretty straightforward once you're pretty well practiced with Gauss's law. So once you've got that well in hand, then maybe things aren't too bad here. Okay, this comes out pretty nicely here. Okay, so as mentioned before, that there might be a another way of doing this in terms of energy. And so how do you do this using something like energy here? And let's kind of give this a try here. So method 2, we're going to use energy to do this. Okay, so as I recall, there was sort of this energy statement that we had when it came to a parallel plate capacitor that looks something like this. I could scroll back up, but I think there was a 1/2, there was an epsilon 0, then there was the electric field squared, correct? And then there was the volume between the plates. And for the most part, that form right there of E squared times volume just really kind of works for any type of capacitor. So once again, I think most physicists remember that energy stored in the capacitor goes as E squared here. Now I have something here that has E, right? I've already found that, and so that's back here, and so that's a Q times a K, or really 1/4 pi epsilon naught. And so I'm just going to kind of put that in and see what happens here. So let me just kind of leave this 1/2 as epsilon naught. And the electric field was Q all over 4 pi epsilon naught, and then r to the -2 here. Okay, and then we can't forget that it's squared. Okay. And so you might kind of start getting a feeling of what I'm going to do here. What I'm really going to do is kind of integrate through the volume and get all of the energy that's sitting in this electric field in that volume. Okay, and so this volume right here, for me to integrate over it, I'm really going to think of that as a dV, and then I'm going to add it all up. And so if I'm adding up spheres, and I want to get the total volume, what I need to do is get the surface area of the sphere and then change its size a little bit, right? Go from like a 4 pi r squared, that's the surface area, and then change the r to dr, and then you have a little bit, right, more, and then you kind of keep adding that up. And so my volume here, if I'm going to really try to add all this up, it's going to be a 4 pi r squared. Then I'm going to change the size of that a little bit. And so this should make sense here, right? Because this is a meter squared, and then I'm going to change this meters. And so that gives you really a volume here. But then you can, really kind of add up all of your contributions here. Okay. And so that's really kind of the idea here of what you're going to do. So once again, I think maybe I mentioned that a lot of times people will talk about the energy density, right? The energy per volume. And they're kind of going along, the lines of something like this here. So let's kind of see, let's just be very careful here with a lot of these terms and see kind of what's left over here. So you're going to have a Q here, and it's squared. And maybe you have a 4 squared, you have a pi squared, you have an epsilon squared. Maybe you have an r to the -4 here. And then I'm going to multiply by a 4, a pi, and an r squared there times the dr. So eventually I'm going to integrate this in. I'm just going to try to see exactly what it is that's going to get integrated. And so maybe that 4 there cancels a 4 there. This pi goes away and it takes out a pi there. This epsilon 0 takes out an epsilon 0 there. Okay, and then this right here, that's really the same. Oops, come on, pen. As 1/r to the 4th, and then I have an r squared here. So this is going to take out 2 of those. So I think when all is said and done here, what you're looking at is a potential energy function here that has a 1/2. We have a q squared. You have a 4, there's a pi, there's an epsilon 0. So there's a k there. And then I think this has gone away with a couple of those. So I have r to the -2 dr, and I'm going to integrate that. And so I'm going to integrate that from R1 to R2 to get the total volume here. Now all of this stuff right here are these are just essentially constants once this thing is all charged up here. So all of that's going to pass through here, the integral sign. And so I've got this r to the -2, which is going to be easy to integrate. The power is going to go up by 1. I'm going to divide by the new power. and you know, kind of see you know, what's left here. And so I've got this potential energy here. So I've got this 1/2. There's a q squared there. I think I'm just going to leave this as 4 pi epsilon naught for right now. And then, you know, when you integrate that right there, that becomes r to the -1, and you divide by the new power. And I've got limits of integration. I'm going from, you know, one plate to the other plate here. And so this right here, I'm going to bring this as a minus sign out front. And I've got then 1 over R2 all over minus R1, you know, something like that. Okay. Okay, so, you know, there's a lot of ways I guess we can play with the algebra here. What I might do is maybe take a sneak peek and, okay, so up here we have capacitance is, there's kind of an R1 minus an R2. And so I might get this minus sign here now and maybe actually kind of maybe put it in here, which then is going to, if I multiply by a, you know, a minus here, it will reverse, you know, the order here of what's taking place. So that will become positive, and then this term will become negative. Okay, and so there is, you know, a potential energy function, you know, in this volume of space here. Okay, so, you know, where do we go from here? Well, we haven't done this with energy yet, but, you know, I'm going to, you know, revert back to general energy statements that will really kind of work for any kind of capacitor. So not to get you seasick, but I'm going to, let me see, I can remember 1/2 CV squared. I think what I'm going to use is, I'm kind of looking at the terms here. I think I'm going to use this one. That potential energy in general could be written as a 1/2 CV squared. That's not really the one that I want, but as a 1/2 q squared all over c. So that was one of them that we had earlier in the lecture. So I think, you know, I'm going to probably try to use that here. Okay. So if yeah, so you know, this is for the system that we've got, and this is kind of in general. And so I think what I'm going to do, I'm just going to set those two things, you know, equal to each other. That I have a 1/2 q squared all over c equals a 1/2 a q squared, and then there's a 4 pi epsilon 0, and, you know, the rest of this business with the difference between the side, you know, how far the plates happen to be. And once again, you know, capacitance, you know, usually there's no Q's in there, so that's kind of nice to see that go away. You know, this 1/2 takes out that 1/2, and you know, what you're left with here is 1 over c equals, so that's gone, that's gone. There's a 1 over 4 pi epsilon naught. Let's try not to lose anything here. And so this is not the answer. I need to take the reciprocal of both sides. And so when you do that, you know, this side is easy. This over here would be a 4 pi epsilon naught. And then you've got to get all of this stuff here and, you know, flip it upside down. And so you really kind of want to do is get a common denominator and kind of turn that upside down here. Because it's, well, or what you can do is think about it, all that all over 1. And, you know, you could write it, you know, this way. And so, you know, we could have, you know, some sort of statement like that. And, you know, at least algebraically, we should be able to show that it equals, you know, what we had before. And so 4 pi epsilon naught all over, you know, looks like 1 over R1 all over 1 over R2. I don't have to do any algebra. Okay, looks like they're already equivalent. So Once again, so there's a couple ways of going about doing something like that. One is through energy, and then one way is going to be, what I'm looking at right here, of going through the steps of get E, get V, and then be able to get something like the capacitance through a general statement like Q equals C times V. Okay, very cool. Okay, so maybe lastly, the other type of capacitor that is fairly well known is a cylindrical capacitor, and someone is saying find the capacitance here. And so I think what I'm going to do is just kind of do the the brute force. I'm just going to find the electric field between the plates. I'm going to find the voltage, and then I'm going to try to get some sort of general statement of the capacitance. In this case, because I've dealt with this before, I'm going to get my Gaussian, and it's got to be in this region here. So my Gaussian is going to be, something that looks like a cylinder, but I'm going to try to make it, the entire length here. They said, this cylinder here is length out. I'm going to make my my cylindrical capacitor exactly that length on my Gaussian, just so that I get all of the charge enclosed and things like that. So a lot of times, that just makes life just, one step easier. So it's kind of well worth doing something like that. But, my first step is really get the electric field, between the plates. And so I would have this Gaussian here. And, this is not something that we haven't done before, so I might kind of go through this kind of quickly. I have two end caps, and I already know that the electric field through those will be 0. If that's not the case, that means we've got charge and, once again, perpetual motion up and down, that inner conductor. So it's really the electric field from the charge that's enclosed plus Q. It's got an electric field that's going outwards, and the area vector is also in that same direction. And so you end up here with E, as long as you are a certain distance, right? And so everything is here measured from the center line. As long as you don't change your distance from that center line, so let's call that R because it's kind of like a radial distance. As long as you don't change that, E is going to be a constant. And so it's really just the kind of the cylindrical part of the Gaussian here is the part that's important. And so its area is 2 pi r. So that's the area of the circle times the length. And I'm going to make my Gaussian the total length of the capacitor. That way I get all of the charge. I get plus Q kind of inside of there. And so I think we're looking at something here that is no different than anything that we've seen before. That E is going to be all of the charge per all of the length, and then we have some constants here: 2 pi epsilon 0. And then we see a 1 over R, and this is outwards from the cylinder. 1 over R dependence here. And the reason I kind of wanted this is because, this is typically what people call lambda, the charge per unit length. And then you have a 2 pi epsilon 0, 1 over R. And so there's the electric field, and this is, pointing outward here. And maybe I'll just forget the unit vector here since I already have the word outward there. Okay, so this is what the electric field here looks like, and then my second step here is going to use that to get the voltage difference between the plates. And I'm going to use, my general definition here to do something like that. And so I've got the electric field, sitting here in front of me. And so, this is not, terrible to do. We have this built-in minus sign. And I'm going to go from, now on this case, they called it, what they called it A and B. So the inner radius of the inner conductor is A units, and we go out to B. So that's in between the plates here. So maybe I'll start at A and I'll go out to B. And if I get a minus sign, eventually they get capacitance. I'll just take the absolute value because capacitance is never a negative number here. And my electric field is all this monkey business we have up here, which is really a lambda all over a 2 pi epsilon 0 and r to the minus 1 times dr. And so this is not awful to actually integrate. A bunch of this stuff will come out here for free. But you've got this right here, right? And so how do you do that? The power goes up by 1. So from like -1, you go up to 0, then you divide by the new power, 0. And you can't, right? You can't divide by 0. So this is really why you have to invent a whole new function that allows you to do this. And, that should not be really a surprise probably to you. You should know what that function is, I believe. And so you get the natural log of, which is the definition of, the integral of, 1 over x dx. And then I have to evaluate it at the endpoints. And so you have the natural log of b minus the natural log of a. Maybe I'll just write it compactly somehow like this here. Okay. What you might want to do is just kind of take a quick look here that b is the bigger radius. So it's a bigger number here, right? And so if b is a bigger number and you divide it by a, that comes out to be something bigger than 1, right? So if you take the natural log of anything bigger than 1, that turns out to be positive, right? So the way that this is written right here, I'm pretty sure that this is a positive value. And so that minus sign right here, I'm not going to really consider that when I go to my third step of, get C from Q equals C times V, because C has got to be a positive number. Okay, so how do we do that? Q equals C times V. And I'm going to put right in here what V happens to be equal to. And once again, I just have never really seen people talk about capacitors and having some sort of general function that has Q in it. And so lambda stands for the charge per length. So I think I'm going to put that in there so I can get the Q's to cancel. And that's pretty typical. And once again, that minus sign, I'm just going to disregard that. I'm going to take the absolute value here of the voltage difference here. So I really have Q all over L. That's this lambda right there that I just circled. And then I have a 1 over 2 pi epsilon naught, all times the natural log of B all over A. Okay. And I'm really looking for the capacitance. And so you have to solve this for that. But kind of what you want to see there looks like is, that Q to really disappear here. And so I'm going to multiply both sides by, looks like L. Multiply both sides by 2 pi epsilon 0. Divide both sides by the natural log here. And I think that's what C equals. So let's make sure I didn't forget any parts. So that's going to get multiplied by both sides. So that's over here. That got multiplied by both sides. And so did that. And so this looks, not bad. This doesn't look familiar to me. And I might change that to something that looks a little bit more familiar to me, but I think there's really nothing wrong with what we've got here. And so, remember that K equals 1 over 4 pi epsilon naught. And I think that's probably a little more familiar form, is to maybe have this one in terms of K here. But I kind of like what I'm looking at here, because I'm seeing geometry of the capacitor, and that's L, and then the size, the radii of the cylinders. And once again, I see epsilon zero, the stuff between the plates here. And so, what I might do here, just to get in a more familiar form, is multiply the top by 2, and then multiply the bottom by 2. And so on the top, what I have then is L, and then I've got a 4 pi epsilon 0, and on the bottom you have 2, natural log of B over A. And so that's starting to look a little bit like a K here, but not exactly, right? K is 1 over 4 pi epsilon naught. And so maybe that's the reciprocal of K. So I think we can, write this as L, and on the bottom, that's where the K goes. And then we have the natural log of B over A. So this might be a kind of a compact way of writing this, for a cylindrical capacitor. Okay, so once again, there's the geometry of the cylinder, right? How long is it, and what are the radii? And so the capacitance is always seems to be geometry dependent. And then, here is, material or no material between the plates. Eventually, we will put some material between the plates here. And so there's a considerable more to discuss here of, with capacitors. And one of those things is, well, what if we change the material between the plates? And instead of just having vacuum between the plates. And probably I would think most capacitors built have material between the plates. And so it'll be an easy thing to actually for us to change once I think we understand really the physics of what's taking place there. And then, there's probably some work to do here with, what happens if you have a bunch of capacitors being charged up by a battery. And there's different ways of connecting those. And the way you connect them really turns out to make some differences. So there's some interesting things there. So there's some very, very nice physics here for a very simple device, right? Just a couple plates of conductive material set apart, and we put some charge on there. And but using our fundamentals, electric fields, voltages, energy, and so forth, really are always the important driving concepts that allow you to be able to do all this stuff here. So, it might be, kind of good for you to go through and look at the different types of capacitors here, and then see if you can't kind of go through these steps and, be able to do something like this, because there's really nothing here that's, that tricky or anything like that here at all. So, I think this might be a good place to stop for this first lecture. And then we'll take a look at what happens when you put material between the plates, and then how you combine, different capacitors. It may be, when you're connecting to a battery and things like that. And we'll sort of see how to take care of those issues here. So hopefully this helps you, kind of get through some aspects of, the chapter on capacitors. And there's certainly more to do here, but I think, this is a good stopping point for today. So I will see you soon, and hopefully everything is working okay for you. So.